Dear colleagues, dear guest, Mr. Chairman, Professor Dimkić, it's my pleasure and great honor to have opportunity to speak here. I will speak about climate change and impact on water resources in Serbia. To which questions we will try to give some answers. Which climate changes have been already recorded in Serbia? Did they have some impact on river discharges and water resources? What could be expected in the future? What should we do regarding adaptation measures? The topic of these presentations is an assessment of the decline in average annual and monthly river discharges during low flow periods and their correlation with derived temperature and precipitation data and trends. Each prediction, including regional climate model predictions, is sensitive to assumption, uncertainties, and calculation imperfections. The quality of the predictions grow with increasing validation, especially for near future period, by recorded data and especially by trends. Of course, we must distinguish long-term and observed trend for one fixed period. To assess past climate trends, 26 temperature and 34 precipitation stations were selected. The annual average temperature trend in Serbia was found to be about 0.6 degrees Celsius per 100 years, while the annual average precipitation trend was slightly negative. And you can see on the graphs the spatial distribution with trend adjustment for Serbia. The period selected for analysis is from 1949 to 2006. This period, that's important, is convenient because it is relatively long. Data are available from numerous monitoring stations, and they exhibit a close similarity to estimated long-term temperature and precipitation, and particularly river discharge trends in Serbia. Just for example, one convenient period is also 1950 to 2004. You can see that the graphs are quite similar for Serbia. And just for example, the period which is extreme and long-term totally not realistic, we can see here. First graph show data series of 35 years. Next one in observed trend was wet for increasing for whole Serbia. The second one is decreasing much more than realistic for whole Serbia, also quite long series, 47 years. And the last graph shows the series of 61 years, and the longest available at that moment. And that's the graph is important because it shows that sometimes the longest series that does not mean the most close similarity with the long-term trends. Regarding intra-annual trend in Serbia, we can see in the table here the precipitation is relatively positive, or better to say, have increased trend from April to September, especially for September. It will be shown in the graph later. And during the colder part of the year, from October to March, the decreasing trend was found. Regarding the temperature, we can say that September, November, and December are the months with the decreasing trend. April is about 0, and in the other months, increasing temperature trend was recorded. How it looks spatial in Serbia, we can see on this slide that's first 6 months of the year and the second 6 months of the year. Regarding precipitation, the same first 6 months and last 6 months of the year. The September is the month with the most consistent increasing trend in Serbia. What about hydrology? Of course, Serbia, especially its eastern part, experiences a downward river discharge trend. However, contrary to climate parameters, it is quite difficult to specially generalize because several factors affect these trends. Some of the most important factors are the size of the river, the transfer of water, if any, between catchments upstream from the station, the volume and the way of water used by the men, the presence or absence of river reservoir upstream from the station, any land use changes in the catchment, and of course climate change, including differences from region to region. That's observed hydrological data on the average annual level. The left side represents the west part of the Serbia, and the right side represents the east part of the Serbia approximately. One very approximate geographical distribution of the downward average annual river discharge trend is shown on this graph. It should be noted, and here it's underlined, that within all river discharge trend lines, there are rivers and monitoring stations which often exhibit significant trend variation, both up and down from the results of the graph. As a result of the factor 1, 3, 4, and especially 2. This figure was compiled based on the trends recorded at selected 18 river monitoring stations, where factor 3 and 4 were assessed as having an acceptable degree of impact, and where factor 2 is negligible. What's happened during low flow months? From July to October, we have recorded much favorable trend than the average of the year. The average of the year, average in Serbia is about 30% per 100 year, while during low flow months it's slightly negative. In September it's positive, according to positive precipitation trend, and of course according to existing on many rivers reservoirs which equalize the flow during the year. What is to be expected in the future? Well, it should be one box, okay. We have input and we have output, and we try to connect them, and models become more and more sufficient and more better regarding this. But always we have question: did we forget some important things or not? And I will try to present you another approach, not to say another, it's well-known approach. It's a black box here, and to analyze stochastically what's happened with the average entry, in this case temperature, and the average exit, in this case river discharge or precipitation. This slide is important. After that, I will go faster. For each of the rivers, we calculate relative values of average annual river discharge, and annual sun precipitation, and annual average temperature. Of course, relative value for precipitation and river discharge is a quotient between represent average year data and average of the whole period. And for temperature, it's differences between the same categories. Relevant data were grouped into categories depending on deviation of average annual temperature in categories of 0.5 degrees Celsius. Average values were calculated for each class, and the obtained points were used to construct a graph of the dependency between the deviation of the average annual temperature and the given quantity. The graph shows the obtained linear trend and the coefficient of determination R square. Regarding the impact on river discharges, on this table are the results of 14 selected rivers, or better to say, coefficient of determination is shown on this table, and you can see that is quite high. From the lowest is 0.668 and the highest is 0.99, and the average is almost 0.9. On the graphs, on this slide, you can see first two rivers, the results of this analysis, and on the next slides, you can see next 12 rivers. But what else we can do? Even each of 14 studied watershed exhibits specific features. There is no dramatic differences between them. All show the expected trend of an average decline in stream flow with increasing temperature and vice versa. It is therefore fully justifiable to synthesize all relevant data into single data series. Why we do that? This enlarges the data series by 58 members to more than 800 and decreases the effect of random, no standard years, especially in classes which otherwise we have few data points. First graph shows this relationship. Also, the second, just on the second graph, we have changed the ordinates because it's more convenient to have river discharge on the vertical axis and temperature on the horizontal axis. You can see that on this way, with synthesis of all data, we have coefficient of determination 0.97 for linear trends. Just not quite reliable, but it's good to say that if we make 3rd-degree polynomial line, we have very, very high coefficient of determination. If we take a risk to extrapolate this graph to 2 degree of Celsius, that means if the temperature will increase 2 degrees Celsius, in Serbia we can approximately expect it without dramatic change in human activity about 50% less water in our rivers. What about distribution of differences between observed and calculated relative discharges? For all pairs of data relative temperature and river discharge, we calculated relative annual discharge using formula from the previous linear trends. For all pairs of data, we calculate differences between observed and calculated result for that year, and then we group them into the classes, count the number in each class, and the resulting graph is as follows. These graphs, we can say, it's quite similar to one Gauss distribution related to this subject. What's happened in Europe between temperature and precipitation if we do the same methodology? We have here 4 stations on the South Europe, 4 stations on the Middle Europe, 4 stations on the North Middle Europe, and 4 stations on the North Europe. South Europe, it's Mediterranean zone, Spain, Italy, Balkan countries. Middle Europe, it's Austria, north part of Slovenia, Czechia, Slovakia, Romania. North Europe is Denmark, North Germany, Poland, and North Middle Europe, sorry. And North Europe is Scandinavian countries and North Russia. You can see that on the above graphs for South Europe, we have dominant graphs which show the decreasing precipitation trend with increasing temperature. And as we go to the north, that's change, that we have increasing precipitation trend with increasing temperature in that year, and that's absolutely in line with IPCC scenario for Europe. This graph is another 16 stations with the quite similar results. Jaroslav Černi Institute has taken part in one international project with name Climate Change and Impacts on Water Supplies, CC Waters. In that project, 18 institutions from 9 countries from Southeast Europe have worked 3 years, and about 20 test areas were analyzed with different types of water resources. In general point of view, the central part of Southeast Europe, that means East Hungary and Serbia, West Romania and Bulgaria, are the most vulnerable zones, with many parts in Mediterranean coastal area, especially where the demand increase during the summer. The chosen test area and the conditions inside them are too much different, so the results cannot be generalized easy, even if they have very similar climate change expectation. That means, in many concrete cases, that regional water systems will be necessary to bring the water from the area with sufficit of water to area with deficit of water. Some of these regional water system in Serbia has been built in the last 15 years. And these 3 graphs are the results, some maybe of the most interesting results from this project. The first graphs show expectation regarding renewable water resources in percent regarding the present availability for the period next 30 and the end of this century. The second and the third graph is represented the exploitation index, which means the quotient of water demand and availability of water resources. First graph represents exploitation index related to total water use, and the second graph related just to drinking water supply. We can see that because of the great variability of the test area, some of them have already met water shortage or are close to water shortage. Another project where our institute is involved, we have heard today many times, is ICPDR, and I want just one slide to show from the results of colleagues from Germany who have analyzed all available studies related to climate change in this part of the world. And that's the graphs which show what's happened with uncertainty of the prediction of some events. And we can see that temperature is very high expectation related to their increase, also some other issue. And what I want to underline is that droughts are also very expectable for this part of the year, or better to say, certainty about them are higher than the certainty about the floods. That doesn't mean that the floods cannot happen, that just means that the certainty about floods are less because of the generally precipitation decreasing expected trends. And of course, we have increasing extreme events, and that's about that. Conclusions related to temperature and precipitation in Serbia, I will not repeat almost all I have already said during the presentation, also related to hydrology. What I want to say is what should we do regarding adaptation measures in Serbia. Related to support global effort to reduce carbon dioxide and to make other good things related to water management and forest management, is that forest management and forest planning become quite important. Related to adaptation measures against water shortage, in addition to very important water rationalization, some of existing regional water system must be upgraded and some new must be built. In that case, Serbia will have enough water for water supplying in any climate change scenario for at least next 50 or 50 years. Who can perhaps benefit from the outcome of this research? Apart from Serbia, it is believed that the presented results will be of interest to the entire region of Southeast Europe. The results indicate that an in-depth study of all the observed data should be undertaken parallel with regional climate model production. And ultimately, the proposed methodology for the assessment of average temperature impact on average river discharge and precipitation could certainly be applied in many parts of the world, especially in regions where a long-term decreasing precipitation trend is recorded. Acknowledgements to our institute, to Directorate of Water, and to Ministry of Science. And for the end, one nice picture. Thank you.